Folks join in, but we're going to go ahead and get started to make sure we stay on time. This presentation is titled What You Need to Know About the Windows DNS Vulnerability, and the lead presenter for the session is going to be George Orchies, who is a SANS certified instructor, is the author of our red teaming class, and is the CTO at Scythe. So George, do you want to go ahead and take it over?
Thank you very much, Steve, or Sims, like I like to call you. And thank you for pronouncing my last name correctly. That's always nice to hear. And welcome, everyone. Thank you all for joining. The first question I generally get is, are the slides available? So I will go ahead and just say yes, they are. I just posted the link on my Twitter. It is on Slideshare. You can follow along, and if you have any questions, you can post them on the Q&A here on Zoom. Thank you for that intro, Steve. As mentioned, I'm the Chief Technology Officer of Scythe. I wrote the 2-day Red Team Exercises and Adversary Emulation course for SANS. Been teaching for SANS for over 10 years now. Can't believe it. When you say it, it sounds real. Also co-creator of the C2 matrix, command and control matrix, if you like that sort of stuff. I spent 10 years at Citi running the offensive security team, which involved a lot of vulnerability management, a lot of exploitation, a lot of O-days, and pretty much all this fun stuff here that we're going to talk about. I am or was a voting member of CVSS, so version 3 and 3.1. You can thank me for, and the team there. Obviously, I'm not the only one, but definitely see a lot of, oh, why is this CVSS score high or low or medium? And there's many things there to work on, of course. So version 4 is being worked on. Make your voice heard. It's a first group. You can go and let us know how to improve that. Also, like ISSA and NSI, I'm a technology fellows there. Do want to take a quick second and thank a few people. Johannes Ulrich, who runs the Internet Storm Center, thank you for the technology review. So I don't just write these presentations up, I actually have them reviewed by other very smart people. He was one of them. Steve Sims, he'll actually talk a little bit, a couple slides on here about coming up with an exploit for this issue. Chris Trunser, Rob Fuller, Mubix, John Garenflo, all of you, thank you very much for reviewing this and just making sure it's all technology and technically correct. So why are we here? We're going to talk about DNS. I know many of you all say it's always DNS. It's a running joke, right? It's always DNS. In this case, it's Windows DNS Server. So we will specify that and clarify that as we go. We're going to talk about this vulnerability at a high level. Then we're going to deep dive. Now, if you're not that technical, that's okay. We're going to deep dive it for completeness. We're going to talk about what this exploit will probably look like. And then if you're not technical, that's fine. We won't spend too much time on that. We will cover the impact, how this will impact your organization, the patch and the workaround, proof of concept, question mark at the end. We'll cover that. There are some posts on GitHub, so they're not real. The 2 that I've seen are fake, so we'll clarify that from now. We're going to talk about detection. So Florian, shout out to you. We'll show a screenshot there of some detection as well as Cisco detections, incident response, and then open up for Q&A. So welcome again, and let's get to it. So DNS, the domain name system, it is integral to how the internet works. The main job is to query it for and go from a domain name to an IP address. So when you go to sans.org, you aren't actually going to that domain, you're going to an IP, and the DNS server is what gives you that. It's a client-server architecture, so you have a client on your system, it queries the DNS server. If the DNS server knows the answer, it replies to you the whatever request you're requesting. In this case, we're talking about A records, where you want sans.org's IP address, and it provides that for you. Now, very important for this discussion is what happens when your main DNS server does not know the answer to the query that you have. And most DNS servers have what's called recursive queries enabled. If you've read some of the posts about this, they call it forwarding. we like to use the right terms, right? So recursive queries, it will go and ask the next DNS server, hey, do you know where sans.org is? All the way up until it gets to the name server. So that's very important for our discussion. We're going to dive a little deeper into that. DNS does use UDP by default on port 53. Generally, if it's smaller than 512 bytes. If you're using eDNS, then it goes up to 4,096 bytes. If anything's larger than that, then it goes over to TCP, which is also going to be important for this conversation. So this is very basic stuff. You probably already know this. I have here links to the RFC if you want to dive deeper into how DNS works. We're going to cover mostly the vulnerability in this case. So Windows DNS Server, this is an implementation of the DNS server. There's many other implementations out there. We're not talking about any of those. We're only talking about the Windows DNS Server because that is the implementation that is vulnerable. So I repeat, this is not a protocol issue. It is not an issue with the DNS protocol itself. It's an issue with the way that Microsoft implemented it in the Windows DNS Server. Now, Windows DNS, you might say, why would we run a Windows DNS server? And maybe if you're a large organization, you don't have this, but many organizations do. See, DNS is required for Active Directory to function. If you want to authenticate through Kerberos, you have to go through DNS. Do you know what happens when you try to authenticate with an IP? You don't use Kerberos, right? You actually fall back to NTLM version 2. So it is a requirement. So if you are a system administrator, say for a small business or medium business, and you're setting up a domain controller for the first time because you want Active Directory, you will install a Windows Server, you will enable the domain controller, and you will quite easily and trivially be able to enable the Windows DNS Server service. It's very easy to set up, doesn't require much editing of the configuration whatsoever. And again, it's required pretty much in the wizard nowadays if you're setting up like that. And this Windows DNS service runs with system privileges, which is going to be important as well for our talk here. So where do we find this? Generally, we will find the Windows DNS server running on domain controllers, or we might find it on member servers. That means a server that is part of an Active Directory domain. So let's talk a little high level about this CVE. This is CVE 2020-1350. It was disclosed and patched yesterday by Microsoft. So that was released in the patch Tuesday, right? Everyone's expecting these patches to come out on a monthly basis, always on the second Tuesday of the month. In this case, shout out to Checkpoint and Sagi Tzazadik. Don't know if I butchered that. I apologize if I did. For writing this up and actually putting up a pretty good paper there that I reference. And there are references on the last slide. So everything I'm talking about here has references. They're on the second to last slide if you're following along on the Slideshare. So shout out to Checkpoint for being the discoverer of this. They followed coordinated disclosure and they gave it a name, which is SIGRed, SIGRed. And that name comes from the vulnerability, which we'll detail a little bit more in the next couple of slides. At a high level, it's an integer overflow that leads to a heap-based buffer overflow. So it's actually a pretty standard vulnerability. Exploitation gets a little harder, and we're going to cover that in a minute. I see here the question from Stephen Runyon. What? No logo? Yes, no logo on this one. We have spared ourselves from having to have a logo or a custom domain, but we do have a name. Nice pointer there. It does have a CVSS of 10. That means the worst case scenario in CVSS, and it affects Windows Server 2008 through 2019. Now, I do want to comment on that. Microsoft Windows Server 2008 is end of life as of January 2020. We've already started 2020, as I'm sure all of you have noticed. We're more than halfway through, and they released a patch for it. That means it's important. So even if you still have some Windows Server 2008, I know none of you do, but if you did, theoretically, right, you have a patch now available for that, which is nice because most people that run this are paying extended support for this particular patch, and in this case, they don't have to. So it has a CVSS of 10, which of course, worst case scenario, and CVSS scoreland, and affects all server implementations. And the particular process that's affected is DNS.exe. Now, I do want to point out that that is different than your DNS client. Your DNS client is not vulnerable to this issue. Now, you'll see out there that this is a 17-year-old bug. That's just because when it was originally created, it was there, and we just found out about it yesterday. So I point that out because some news is pointing that as well. Now, your systems will be vulnerable if the Windows DNS Server service is enabled. That doesn't mean all your Windows servers have this enabled. You will actually have to go check and see if the Windows DNS Server service is enabled, and that is where you're going to want to focus on. Now, to exploit this, it is not about sending a DNS request. It actually comes from the DNS response. So we're going to dive into that a little bit more, but that's want to make that very clear. Some of the write-ups I've read, even the checkpoint write-up at first lists a request. They then clarified that it's not in the request, it's in the response. And Microsoft does not have any evidence of active exploitation as of right now. And right now is Wednesday, July 15th, I think. So the attack vector. The issue is with the DNS server service, DNS.exe, and in the way that it parses the response that come in from recursive queries. So again, your endpoint requests to look up some record. It goes to your Windows DNS server, which is configured automatically on your system, right? Everyone has a DNS server configured. If that Windows DNS server does not know the answer, it will then ask if recursive queries are enabled, which they most likely are. It will ask the next server and the next server. It might actually go out to the internet, might go to Google's 8.8.8.8 or to Cloudflare, or to any of these other DNS servers, but eventually it will get to the authoritative DNS server of the domain you asked, which is called the name server. That host, which is controlled by an attacker, can send a specially crafted response that will follow that same trail down. When it gets to the Windows DNS server, it can exploit this particular vulnerability. Now, it's not any response that will do that. It has to be what's called a SIG resource record. And that will trigger because it will be parsed by a particular function called query sig wire read. And we mentioned that this is a pretty basic integer overflow because it is. Anything larger than this 64 kilobytes would trigger this particular vulnerability to be exploited. Now, there is some talk that this can be triggered through Internet Explorer, and that is correct. That's because of the connection reuse and pipelining features, which that if you use Internet Explorer or a non-Chromium version of Edge, you can actually go to https:// whatever bad DNS:53, and it will go and pull this information. So it can be triggered through there as well. And that's important to point out because the Windows DNS server does not need to be exposed to the internet, doesn't need to have port 53 open to the internet. Just take someone on the internal network that does go through a Windows DNS server to open one of these links. Again, worst case scenario. So let's dive a little deeper into this particular vulnerability and this issue. And it is with the DNS query and more importantly, the response, right? So DNS payload sizes are generally 16 bits and they're only used for DNS over TCP. There is a query ID. So some of you may ask, why can't we just send a response to a DNS server? The answer to that is because a DNS server uses query ID. So every query has a query ID. If it gets a response that doesn't match that query ID, it will not accept it. And that's important to know as well. So you can't just send this response remotely from the internet to some DNS server and exploit it because of that. Then there's flags. There's a number of queries, number of answers, number of authority records, number of additional records, and then our resource records. And you see the resource records here are a little bigger, right? And that's a visual representation that the length varies. So the resource records is where we're going to start looking at. That is where you can augment the size of it and possibly trigger the overflow. So if we look at normal DNS pointers in the response, DNS responses generally have repeat names, right? And DNS is actually really good about that. It's not going to go out and search the same thing if it already has that answer, for example, through DNS caching and things like that. But in this case, we want to talk about saving space with the pointers. And it can be used to save space by pointing to a prior copy of that name. And that's going to be important here as well as we try to exploit this vulnerability. So what would it look like? Well, you have some end user go out to a domain. It goes through your Windows DNS server, goes through recursive queries, eventually gets to this malicious name server, which will then send responses. The response is now received by your Windows server. That's step one here. Then the RR, right? This register, the response, and the particular function is called dispatch function for type, selects the way to handle that. If it's a SIGRed, that is passed to a function called SIGWire-read. It records that size if passed as a 16-bit integer. And that's a big if, right? Because what if the pointer is larger than that? What if it exceeds those 16 bits, also 64 kilobytes, right? The 64 kilobytes is going to be important for us. Then it expands that. And DNS.exe only allocated 64K for this. So if it now received more than that, it will get copied into there. And of course, memcopy comes up, right? Which copies a larger data stream, right? Over 64K into a buffer that only allows 64. And there you have your heap buffer overflow. So it's actually a pretty straightforward heap buffer overflow, but it's a lot harder to exploit. And for that, I'm going to bring Steve Sims on, who's actually done some work diffing this, and of course writes the 760 class, which dives way deeper into diffing and finding these exploits through vulnerable code.
Yeah, thanks, George. Real quickly, I don't want to take up too much time. A lot of what I'm going to say is based on a little bit of diffing and reversing that I've done, and some of it's based on what I read in the paper, so I haven't been able to go through and validate. I probably should have stayed up all night and worked on getting a working exploit, but last time I was working on doing that was the Crypt32 vulnerability in January, and I was beat by many other people who are way better at crypto than I. So I figured by the time I wake up, someone's going to have a working exploit. And now I'm like, I wish I would have stayed up all night. So I'm going to continue down this rabbit hole. But I apologize for not cleaning up this pseudocode here. This was using Chris Eagle's BLC port of Ghidra over to IDA Pro. But if you see the if statement down towards the top middle area, you can see pretty far into that there's a uvar1 equals, and then you've got packet name to count name. That right there gives us the opportunity to do the integer overflow because we have control over some of those parameters. And what that's going to result in is an allocation that is way, 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 way less than the 64K. And then what we can do then is control the size that's passed as an argument to memcopy. Memcopy, it's usually involved in a lot of vulnerabilities because it all depends on where it's getting its size argument from. So we can then, since the allocation was very small due to the overflow in the integer, we can then do a memcopy size that's greater than what was allocated. And that's going to allow us to write out of bounds on the heap. Now, if you can skip forward, in the actual paper, I saw that they were able to get control of the address that's being called, an indirect call, which is leading to a control flow guard catching it. And what's probably happening there, again, this is guess, I haven't gone in and validated. And what you're looking at here on the slide, I decided to diff or use the 2008 server one because it felt good to do that since it's no longer supported. So that's why you see 32-bit registers referenced here. But what I think might be happening, have not validated, is that with this out of bounds write, with the memcopy call, you're able to overflow something, which there's likely C++ objects or other things in memory on the heap. And more than likely, you're able to overwrite something like a function pointer, maybe a virtual function table pointer, a V pointer, so that when you write all this data out there, what's being called is what you've written. So in the paper you see, I think it's like 4343, like a bunch of C's or something that's being called. And so control flow guard at that point is catching it because the address that you're telling it to call is not mapped memory. Not only that, control flow guard creates a bitmap that basically says, okay, in order to go to an address, that address has to be a valid function entry point. Now there's some constraints there, there's limitations. Control flow guard doesn't solve all the world's problems because it's not so granular that it's the specific addresses. There's some alignment there. So what control flow guard does is greatly reduces the number of return-oriented programming gadgets that can be used because those addresses that you're using of the ROP gadgets have to be pretty close to a valid function entry point for it to work. So at that point, if you're able to get control, you would want to find ROP gadgets that are within the same area of a function entry point and go to there and kick off your ROP chain, which of course would probably be something like set up a call to virtual protect or virtual alloc to change permissions in memory and try to get shellcode execution. So you can probably get around control flow guard if you can find enough gadgets, but before you can do that, you've got to get the memory leak. And they also in the paper show that you're able to read some data out of bounds where you can get a memory leak, which means that you can probably, if you find something meaningful, which I'm sure you can, calculate the base address of some DLLs. So more than likely there's going to be some address that you can leak out there that you can find its relative offset within a dynamic link library, and then you can subtract to get the base address, and then you'd be able to calculate your ROP gadgets. But again, you've got to take into account control flow guard. So again, exploitation is going to take a little bit of time, but it seems pretty straightforward, and props to Checkpoint for this. I mean, it's an easy bug. It's a really easy one, and it's nice. I mean, I haven't seen one of these in a while, and I think this one's going to be cause pain for many years to come. I'm already like planning on putting it into my 760 course because that's going to be a fun one. What you see on the slide here, on the left, this is using bindiff, and on the left you see the unpatched version. On the right, you see the patched version. And on the patch version on the right, you can see down in there that there is a check. It says compare EDI to FFFF. So we're checking to see if 65535, and then below that you see a jump if above, and there's a couple extra checks below that as well. But the point is you're not going to make it to that allocation, the RR allocation function, unless the size is correct. Otherwise you're going to jump. So that's a little check that was added. So I think that's it for me, George.
Awesome. Thank you so much for that, Sims, and good luck if you get it. Definitely hit me up on text. Bringing it back, if you're not looking and diffing at this, no worries. We will continue on and talk about impact and a few other things. One thing I do want to talk about is the word wormable, which we got bingo yesterday. If any of you are playing 2020 bingo. We hadn't hit Wormable yet this year, so here it is. And what does that mean? Well, that means a malware or an exploit that can replicate without user interaction. So generally, it's an exploit that does not require authentication, that allows remote code execution, that execution is with some privilege, in this case system, and that it's used quite a bit by a number of systems, and most systems have a DNS server configured. Sorry about that. Shout out to Marcus Hutchins, if you know who that is. If you don't, excellent article on Wired by Andy Greenberg. He's malware blog, and he wrote, while technically wormable, it seems unlikely. A more likely scenario would be ransomware actors using it to gain access to a domain controller and then pushing ransomware to all network clients. And I completely agree. But for completeness, let's look at possible impact. If you have a DNS server on the internet, and in particular, a Windows DNS server on the internet, then that means, and you allow queries in, and those queries can be recursive, then you are at higher risk, right? We don't believe there's many of these, but this is probably worst case scenario. Look into it. What would happen if someone compromised your DNS server? Well, they would probably now have access to the internal network. And if that DNS server that has port 53 exposed to the internet is also resolving for internal systems, then the attacker will have control over any response, meaning that they are now a malicious person in the middle. Another impact here is if you're running the Windows DNS server on a domain controller. That means that an attacker will now become and have system privileges on your domain controller, which means the entire Active Directory should be considered compromised. With full access to Active Directory and on a domain controller, you will be able to pull all the passwords of all users in that environment. You'll be able to send malware to any system in that environment. You'll be able to modify anything, pretty much your entire network. And again, worst case scenario here would be compromised. Lastly, if you are running Windows DNS Server on a non-domain controller, on a member server, it's going to get system level privileges there. So generally what an attacker would do in this case is it will then dump credentials, see if there's any other user with privilege on this system, and use that to move laterally. Now, I'll talk about exploitation, what I would do if I was malicious and found an exploit for this in a couple slides. I do want to, just for completeness, talk about impact on the internet. Now, there's two queries here. One is from Rapid7's Project Sonar that says there's about 41,000 internet-facing Windows DNS servers on the internet. On Shodan, I actually tweeted about this and it did not age well. My query was not as good. The folks over at Shodan actually replied to me and said, hey, try this one instead. So I put that query up here, and there's about 22,000 Microsoft DNS servers with port 53 open. So again, these are our worst case scenario systems right now. So what do? We patch, right? Patch is the solution. I know there's a lot of talk about the workaround, but shout out to Mubix, who particularly told me call this out. So I am calling this out and telling you that the best thing to do is to patch, right? There is a monthly roll-up or a security-only patch for all versions of Windows from Server 2008 and above. So I didn't list all those articles here. The link is right here on this slide. Go there, install the patch. And the reason why I say this, one of the fears of patching is the reboot. If you have DNS servers and domain controllers, you have redundancy. You should be able to reboot one DNS server and the other DNS server will take the load for those few minutes that you're doing this. Same with Active Directory. If it's a domain controller, then you have multiple domain controllers. You have that redundancy. So please question, what is the impact of that reboot, right? And we're already a day late. You had last night if you would like doing it over evening hours, but you should definitely try to get this patched and rebooted today. Now, the workaround. There is a workaround. It's a registry edit. And what it does is it limits the size of the response. So you can see here the registry key, the D word is TCP receive packet size, and it sets it to about 65 kilobytes, a little less. And then you need to restart the DNS server service. So that's pretty easy to do as well, right? Net stop DNS, net start DNS, shouldn't be too bad. Now that workaround does limit the responses that you get into 65K. Now, I no longer work at a super large organization where all these little things end up coming up and actually causing concern. So you will need to test that. I have not heard of any problems thus far, but again, better to patch than to apply the workaround. Even after you apply the patch, if you did the workaround, revert the workaround so that you don't have any other impact. I'm getting a couple questions about 2003, Server 2003 being vulnerable. I would say so. Again, this is completely my personal opinion. I have not looked into it. But most likely, the DNS Server service on Windows Server 2003 is vulnerable. If you are using Windows DNS Server on 2003, I highly encourage you to move away from that platform. So, proof of concept. There is nothing public yet that I have seen, and I'm pretty connected. There are two that you might think are there. I even saw a security company blogging about this. These are fake. I repeat, these are fake. I purposely did not put the URL there. So it is funny, it is trolling. If you download something from the internet, please look at the code. Don't just run it. It's interesting to follow both of these folks on Twitter and see what they're doing, because they added what's called a canary token to this code, and they know every time someone runs it. And it's a really sad result. So please don't run these. Both of these are fake. They're fun for trolling, but do look at code before you execute it. Now, Steve talked a little bit about control flow guard, and that is one of the things that makes the exploitation of this harder. As you saw, the vulnerability is pretty standard. It's a basic buffer overflow that we've been talking about since the 90s, right? You take this larger piece of data and you throw it into a buffer, you copy it over into a buffer that's smaller, you overflow the buffer. However, in this case, DNS.exe was compiled with control flow guard, which makes exploitation harder. You're going to have to send a lot more requests to learn about where you are in that environment before you can actually get exploit code. So there is no proof of concept, but we do expect it out at some point. Microsoft rated it as so. They have an exploitability assessment score, and they rated this one as 1, which is exploit more likely. So detection. How can we detect if someone's trying to exploit this? There's multiple ways. I actually have 2 slides on this because it kind of grew over the last 24 hours, which is typical. One of the main things is to look for large DNS responses, right? One is look at your DNS traffic. If you're not already looking at your DNS traffic, it's an excellent point to identify even internal systems are compromised or going out to bad DNS, out to bad domains. Look at that traffic. Now also look at the responses. If the responses are over 64 kilobytes, maybe take a look at those. It's a great opportunity for that. Most queries are small responses. Now, if you do start seeing a large amount of responses, that could be this exploitation for this vulnerability. As Stephen mentioned, you're going to have to interact with it to know where you are in memory. It could also be exfiltration. So DNS is often used as a command and control channel. It's a slow channel, but it is a channel used both for command and control and sometimes just exfiltration. So take a look at those. I mentioned the C2 matrix. You can filter out the C2 matrix only for that DNS channel. You see it over there on the right. There's a number of options to do DNS. And test these out yourself. They're pretty easy to install. Shout out to all the folks there that have created these from SensePost, Bishop Fox, and Facebook, as well as the commercial offerings of Cobalt Strike, Innuendo, and Scythe. There's other things we can do for detection. So this one is a shout out to Florian Roth. Not sure if you're on, but if you are, thank you for all your work. So this one, in this case, is a Sigma rule that is going to look if DNS.exe spawned any other process. So theoretically, if we get some exploit that exploits DNS.exe, it'll probably operate in memory, but then to move laterally or do anything else, it's probably going to execute something else, right? And sometimes you just start with a basic, who am I? That is spawning a different process. So looking at that could help out. Sigma is an excellent project. If you've never heard of this, definitely check that out. Cisco also has some rules for this. It looks for two things: DNS response with a length of 64K or larger, or responses that contain at least one SIGRed, which is 0x0018. Both of those may help you out. And again, it's something you probably haven't looked at before, so take a look and see what you have. Now, a quick thing on instant handling. If your system is compromised, what an actor will most likely do, if they find an exploit for this, is implement the workaround. That is probably the first thing a malicious actor would do. It's the first thing I would do, because if I find a server that's vulnerable to this, I don't want everyone else trying to exploit it, because you're messing with memory. You can, all the risks of exploitation come in, which means you can crash the service. If you crash this service, you're going to blue screen the system because it runs a system. So the first thing I would do if I did find this exploit and got onto a Windows DNS server is I would apply the patch. That way, everyone that's trying to compromise it can no longer compromise it. And then from there, again, look at the impact slide I mentioned earlier. If you're on a domain controller, you must assume your Active Directory is compromised. The rebuild here is not going to be the rebuild that we dealt with earlier this year around Citrix systems, around PAN systems, etc., right? Because this is your Active Directory. Your Active Directory is a directory. It's a database of all your users, all your groups, all your permissions, all your computers. And the quicker you catch them, the better. If they're on there a long time, you will have to assume it's fully compromised, and they'll probably be able to come back through multiple of ways. Now, rebuilding Active Directory, I've done it before, is not trivial. It's a ton of work. You may want to seek some professional assistance. There's a lot of folks that are really good in Active Directory. I'll give a shout out just to adsecurity.org, but there's a number of ways here. And again, I want to scare you and say, oh, you're completely owned, but really it's going to be better that you don't sleep a couple nights to get this fully patched than an exploit coming out in the next few days and someone getting compromised and, of course, doing something and compromising even more systems. So that covers what we have here, what we've mentioned. Again, I like putting references. So here are all the references: the Microsoft original advisory, the workaround, the checkpoint research, the RFC for DNS, Wired's publication of it. That's Andy Greenberg, one of my favorite journalists, Hacker News as well, the Shodan and the Rapid7 lookups, and the Sigma rule there. And as we continue to, as this evolves, right, we will continue to post things on there. So feel free to follow me at George Orchies on Twitter. That's generally where I can quickly share information. Florian is probably good to follow as well, and everyone trying to work on the defensive side. So again, thank you so much for your time. Let me take a look at some of the questions here. Yes, so to reiterate, the exploit has to be on a response, not on a query. Someone mentioned zoomeye.org is showing about 20,000 results as well. Thank you for that. And I answered the 2003 question as well. So yeah, if there's any other questions, I mean, I'll pause for a little bit longer, but I think I've covered all the questions here. So with that, Sims, do you have any, are slides available? Yes, I will reply on here with the slides, and then this recording will be available as well. Another question here: if your DNS, you use a Windows DNS server and it forwards to another external DNS, are you still vulnerable? Yes, because your DNS server will eventually get the response. So this is actually a call. I think it was Mubix that put this yesterday as well, is that one of the ways that we might be able to detect this and stop it is with Google, with Cloudflare, with all those other DNS providers coming together and looking at those DNS responses and blocking anything that looks malicious. I'm sure some of you saw the NSA is planning to roll out its own DNS. Excellent article about that, and actually a video from Dave Eitel, founder of Immunity, on that. And when it's coming back, it will still come back through your Google DNS or through your ISP's DNS. It's the response once it gets parsed by your Windows server is when the exploit would happen. All right, I think I've answered all the questions. In the report from Checkpoint, it shows RCX being overridden. We don't see RIP being overridden. That is correct.
Yeah,
that is. Go ahead.
I was going to say, yeah, that's just an example of an indirect call where the address that's going to be called ends up in a random register like RCX in this case. And if that call instruction were to execute whatever address, which in the paper is like 43434343, so on, that's the address that will be called. But there's a control flow guard check in there in the middle that's catching that address because it's both not mapped memory and it's also out of the control flow guard bitmap table. So it would have to be an address. As long as you were to get into that register, an address that is in the aligned area of an entry point of a function within the control flow guard bitmap, you would be able to gain code execution. So that's when you would see the instruction pointer get that address.
Excellent. Another question here, will Qualys be able to detect this? They should. So any vulnerability scanner that authenticates to the endpoint, to the server, should be able to detect this. There is a GitHub. So I actually tweeted about this about an hour ago. There's 4 GitHubs with this CVE. 2 are fake. 1 is a PowerShell script that checks if you are running the Windows DNS Server service and if you have applied the workaround. I would imagine Qualys, Nessus, Rapid7, all of those will be able to do that as well. Again, that requires you to have authentication onto a system. I know that's generally how most vulnerability scanners work. So the answer to that is most likely, but check with your Qualys rep or any vulnerability scanning solution that you use. Any way a threat actor could send a malicious URL to a workstation in a Windows AD environment, force a recursive DNS query by the DNS server, and result in compromise? Yes, I believe that would be a way of doing this. Yes. You can phish someone and or even go to a website that pulls some other domain in particular. If they use Internet Explorer, that would be the best bet for your scenario there. Okay, I think questions have died down. I covered all of them. Any closing words, Steve? I obviously want to thank everyone for their time. The slides are available already. And of course, the recording of this webcast will be available through your SANS portal.
No, nothing here. Yeah, thanks for everyone for joining, and I'm just looking forward to working on this thing to get code execution. Looks fun.
Awesome. Well, thank you all, and stay tuned, connect with us, and have a great day.